Thank you.
Hi guys, sorry I was a minute late. Just one quick question. So are we going to be presenting the presentations off of our screens, or would you be running it on your end?
No, from your screen. And we have it on our end if you don't have it.
No, I have it ready on my system.
Okay, thank you. And I think Professor Harris we just started the session, so the floor is yours.
Okay, thank you.
Thank you.
Hello, welcome to this session, which is 4A passive data applications. My name is Harris Koutsopoulos. I'm a professor at Northeastern University in the Department of Civil and Environmental Engineering. And before we start, I would like to thank Brandon, Amer, and the entire team at the University of Toronto for putting together a very exciting program and doing such a superb job organizing in short notice this virtual conference, which I think it's going, I never thought it will be going so smoothly and it will be so interactive. So thank you to everybody who has worked hard to put this together. So I would like to welcome the speakers and the attendees of this session. We have a panel, a group of presenters, which is quite diverse from research, academia, from the public sector, from the private sector, and they're going to share their experiences and work on using automated data and other passive data to inform decisions, measure system performance, both from the passenger point of view, but also other aspects, the overall transit market, the network design aspects up to the stop level. So again, I want to remind everybody that most of the presentations are available to download them from the final program that it's posted on the Union home web page. And also, if you have questions, please we'll keep all the questions for the end of the session. And remember, you can enter those questions in the Google document using the tab that corresponds to the session where your question applies. I would also like to remind you that the session is being recorded. So without any further delays, I would like to ask Marcela, who will be the first presenter, to talk about public transport route recommendations using passive data. So please go ahead.
Thank you very much, Harris. I will now share the screen. Okay. Well, this work has been done by Felipe Vera, an MSc student, and myself. We are both from the Universidad de Chile, Department of Civil Engineering at the Faculty of Physical and Mathematical Science. And we also belong to the Complex Engineering Systems Institute. And the question we asked to the data and to the methods was whether we can improve public transport route recommendation using passive data. As you know, there are several applications that provide route recommendation for public transport. Some of them are based on rules, such as the minimum time route, or the one with less transfers, or the one with less walk. There are others that use a weighted time function to adequately consider all the dimensions of times within the trip. And there are others, the more complex ones are based on utility functions, where there is a compensatory function that accounts for the different aspects in the utility of travel. Now, our methodology was to use data obtained from bus GPS and smart card that is processed in a program we developed at Universidad de Chile, which is called ADATRAP. which can recognize the route used by the users, and we can observe all users every day. So we build the consideration set for a particular origin-destination pair using all the bus stop or metro stations that are within a certain area around the specific origin and destination of the trip. So we use observe routes for a particular origin-destination pair, and with that we build the consideration set, which is used to build route choice models. We try different specifications such as multinomial logic, mixed logic, and also we try models with individual parameters. With those models, we make the predictions that are the feed for the trip planner or for the recommendation software. Our city, Santiago, has a large public transport system, which has over 11,000 bus stops, over 300 bus lines. At the time of the data extraction, we had 5 metro lines, now we have 7. Our system is a frequency-based operation. There are no timetables, and people pay when boarding. We use data from the morning peak hour. We use 3 days, Tuesday, Wednesday, and a Thursday. We observe over 2,000 origin-destination pairs. And in average, for each OD pair, there were over 3 different routes. So the utility function we use is very simple and very traditional. We use travel time, waiting time, working time, and the number of transfers. The models we calibrated using this passive data, we obtain significant parameters, and also we obtain significant parameters of the log normal distribution, showing that there is a variability in the perception of these variables by the users. Here are some examples of the ratio between the parameters to compare the models we estimate with also the model from the model calibrated from the last origin destination survey, which was made in year 2012 in Santiago. You can see that the ratio between the waiting time and travel time, and also between working time and travel time, are reasonably similar, but the parameter, the ratio between the transfer parameter and the travel time is much larger in the origin destination survey. So we can see here that we can actually estimate models with this database, and we found some differences with models obtained from surveys. Now, if you look at the individual parameters, we can see that they have a distribution. Some are more spread, some are more skewed, but clearly a distribution of individual parameters can be observed. Now, if we make predictions with these models, we can see that the models, that the simplest rule, which is the shortest path, or the models obtained with the origin destination survey, have a first choice recovery below 80%. And we can improve that with the multinomial logic, the simplest model, but estimated from passive data. We improve, and we also improve a little bit more using individual parameters. So to conclude, we use passive data, spatially and temporally distributed, to calibrate our models. We show that models can be estimated without problem using this type of reveal preference data. We obtain consistent taste parameters. We obtain significant effects of the taste distribution in the population. We were able to capture and we can update with more data individual preferences. And the conclusions to the initial questions is that yes, we can improve public transport route recommendations using passive data. Thank you very much.
Thank you for an interesting presentation and on time. So we will move ahead with the second presentation, which is on interactive dashboard tools for transit market analysis. And the presenter is Pragun Vinayak. I hope I pronounced the name approximately correctly, from Cambridge Systematics. Please go ahead. Unmute yourself.
Okay, can you hear me now?
Yep.
All right, thank you so much. Good afternoon, good morning, good evening, everyone. So I'm going to be presenting on the application of location-based services data for transit market research. This is a very specific application. And before I begin, I would like to give a shout out to my colleagues from Chicago, Amit, Ranjan Mondal, and Jingjing, Salah, and Anurag from our Los Angeles office, who've been instrumental in helping us carry out these studies. So here is the general architecture of the steps that we adopted for each of these studies. And I'm going to present examples from 3 major US cities, Los Angeles, Boston, and Denver. 3 regions with very different travel patterns and very different transit needs. So we begin with the data sets, and there are 2 tranches of data. One is the location-based services data, which gives us measures of overall travel in the region. Now, this data is collected from smartphone applications where the location data is being generated whenever the user it has either the app actively open in the foreground or passively in the background, but the user has explicitly agreed to share his or her locational information with the data provider. So this is a very noisy data set. We start with what looks like breadcrumb data. We run it through heuristics to identify trips and activities. And then we adopt a lot of validation and calibration procedures to finally make these representative of actual travel on the ground. And then the second set of data sets which accompanies the LBS data set are the transit data, which is either the fare card data or the onboard survey data, whichever is available with the agency. The next set is we enrich the data set with some routing information. So we route both the transit trips and the LBS trips through the Google routing engine as well as the OpenTrip Planner to give us the door-to-door transit travel times and the auto travel times. And because a lot of the agencies want to measure the outcomes through an equity lens, we also append equity information to the data sets wherever we can. And the end result is the analytics is packaged in form of interactive dashboard tools. And this is what I'm going to be focusing on today, which allows the decision makers to very quickly summarize, create a lot of summaries, both aggregate and disaggregate in real time. And they have a whole slew of filters available at their disposal to select the specific travel market of their interest. And then use this to support the decision making and the policy making. And we have found that the decision makers definitely have a greater buy-in when they use these dashboards. And I'm going to walk us through a couple of applications in the dashboards that I'll show in the subsequent slides. So I'm going to quickly flip through a couple of the slides that I have for you. So these are the different dashboards that we've built for Denver, Boston, Los Angeles. This one is another one in Massachusetts. And the last dashboard that you're seeing is the most recent one, which we've been developing with Los Angeles Metro to actually measure the COVID impacts. So to give you a sense of how these were used for the transit market research and in particular in helping redesign some of the bus networks to be in sync with the actual demand. This chart shows basically on the x-axis a ratio of the transit travel time to the drive time. So this is a measure of competitiveness. So if transit is slower, the ratio would be larger. So you want to be on the left side of the chart. And the y-axis shows the transit market share. And what we found out was that if transit takes less than twice the drive time, or auto is more than twice as fast as transit is competitive. And we use this benchmark to drive, some of the decisions in tweaking the network. So this animation that I have here basically shows two regions where you see the actual travel demand. So in these two regions, you have just 3% of the demand going between the two yellow regions, and there's a whole chunk of demand going westward and downtown, which is just 1%. The same thing for the other region. But when you look at the transit service, it is still geared towards serving the commute market towards downtown, even though we do not have a lot of trips there. So what we did was, we took the market research that we have, and we reconfigured the bus network, the bus line, to better serve, the demand patterns, more service, taking people to the west side, reduce the redundant service going into downtown, and improve the frequency of service in the areas where it's actually needed. And this one shows the COVID recovery plan. So here we are looking at how different regions in Los Angeles County are reacting to the COVID pandemic. And we are looking at how people, what kind of stores people are visiting using the footfall tracker, which is again an LBS data set. The travel tracker shows how the travel patterns are evolving. So, how much are people visiting during the COVID times, and how is the recovery pattern during these times? And the bottom chart shows you the average VMT. So you can see that a very quick look that, in the week of July versus week of Jan, the VMT has significantly dropped. And these are the guys who are not commuting to work. In Los Angeles, a lot of the trips are long commute trips, and clearly they have been impacted. And similarly, this chart shows the ridership on transit, which, again, fell precipitously, has been recovering in some time periods, but AM peak and PM peak seem to have, had the maximum brunt. In Boston, we looked at... Okay. So in Boston, we just did some select neighborhood analysis to look at patterns by different communities. And the same thing in Denver. In Denver, we were able to, take the existing service, redesign it, and compare different alternatives to see the impact on ridership and some other metrics. Thank you.
Thank you. So the next presentation is from Mark, who is going to talk about how the SORTA system in Cincinnati was reinvented using innovative data analysis.
Thank you. This is Mark Samaan from Cincinnati SORTA Metro. My coworker Waleed is here as well, who worked very heavily on this with me, and he's just going to start it off.
Hello, how you doing? Thanks for having me. As Mark said, my name is Waleed Ismael. I'm a service planner. I just wanted to give you a quick background. We're from Southwest Ohio Regional Transit Authority, also known as Metro or simply SORTA. And we're based in Cincinnati, Ohio. We carry about 14 million passengers per year. We have a fleet of 357 buses and 57 paratransit vehicles. We also have a 46 route bus lines, including both local routes and also express. We operate about 730,000 hours per year. So basically, this analysis is based on reinventing metro system redesign, which is basically a restructuring of our whole network system with the introduction of new routes as circulators and so on. Now, back in 2019, we partnered with Transit app, which provides real-time tracking, trip planning, and fare purchasing in one app for the customers. Through partnership, we gain internal access to the app usage data and obtain over 300,000 unique trips to gain access, to gain insight into how our customers utilize our network. We categorize the data by origin date, time, origin, destination, time, and date. We also anonymize the user IDs. So as you can see, the upper right chart shows the number of trips planned on weekdays. As you see, weekdays is more consistent and higher than weekend, which is expected. And then on the lower left-hand side, it shows the time of the trips that were purchased. As you can see, the afternoon actually is, the peak afternoon is much higher than the morning peak and also the night peak. From this point, I'm going to hand it over to my coworker, Mark Samaan, and he'll take it from here. Thank you.
Thanks, Waleed. So this data helps us get a much clearer picture of how, not only how people currently use the network, but how they would like to use the network when they put their origin and destination point into the trip planning app, and then realize that they either cannot make that trip by transit or that it would take too long. So, you know, we want to get data on the trips that people want to make but aren't necessarily able to do. So with this data, we were able to aggregate based on the GPS locations of the OD, sort of the hotspot origin and destination places in our region. The bottom left map shows the largest areas of demand within our region, with the top 2 areas being our downtown central business district, as well as our uptown area, which is where the University of Cincinnati is, and multiple large hospitals. The smaller dots are obviously places that are in lower demand, but still have enough to warrant looking at. On the right, you can kind of see the what those OD pairs look like. And obviously there's so many of them that you can't really see the region, but this sort of goes to show people are trying to go everywhere from everywhere at different times of day. And we did all of this using ArcMap, ArcGIS software. So we really wanted to zoom in on specific areas as well beyond the whole network to try to get a look at how people are want to take trips within their respective subregion or in their own neighborhood versus the trips that they want to make longer distances outside of their region. This generally matched our farebox and our APC data, but with the addition of folks who aren't riding or regular riders. So this allows us to see how centers of activity emerge within the subregions in our regional area. We further dug it down into the length ranges of trips, of planned trips, to see the difference between very short trips, like less than a mile or 1 to 3 miles, or longer trips, greater than 3 miles or greater than 8 miles. Because the shorter trips typically correspond to everyday travel needs outside of work, whereas the longer trips are typically for commuting or medical appointments or very specialized things like that. So these, you know, as part of our Reinventing Metro program, which is to redo our entire service, we want to look at these short trips very closely to see how we can gain more neighborhood ridership and how we can implement our new service and our new service types, such as circulators and flexible routing, in the most efficient way possible with the resources that we are given. We combine this also with our paratransit data, which is our accessible ride option for folks who cannot utilize the regular transit service. So this is a traditional call ahead, book your trip a day in advance, and then we'll come pick you up within a specific time frame that many American city transit agencies have. But we would like to improve the options for people. So in addition to the transit app data from before, we also focus on where our paratransit riders are going. There are very few specific areas in our region where many riders want to go. There are also lots of small areas, as you can see in the maps on the right-hand side, where people are taking trips that are 1 mile or 2 miles, and the thicker the line, the more amount of people are taking that trip. So we can match this paratransit data to our short distance data from the transit app to see how we can serve both of these populations with one service type or two service types, to give people more options than what we have now, or just the regular call ahead service, which is still going to be available to them. But we would like to offer something better. So using all of this, our region recently passed a new tax levy to fund expanded service. So we are heavily planning what we're going to do with the money. And we have been focusing on, we got regular routes. We know how to plan regular bus routes, but we don't have any circulator service. We don't have flexible service, nor any on-demand service. And we have not changed our bus alignments in 50 years for the most part. So we'll be looking at that kind of stuff, but really focusing on these sort of shorter travel distances within the broader regional network. So yeah, that's what I got. And thanks for listening.
Thank you for the interesting presentation. So we will move now to a similar topic on how passive data informed the development of the Winnipeg Transit Master Plan. Aaron Baxter will share this study with us. Please go ahead and share your screen.
Will do. Thank you so much. I just have to find the share button. No, where did it go? Okay. Can you see the screen?
Yes.
Yeah. Okay. Hello, everyone. I'm very happy to be here at this conference. It's been a great ride so far. I'll walk you through briefly the project that we just finished in Winnipeg in redesigning their transit network and how we used the location-based services devices, or in this presentation, I'm calling them location-based devices, as well as the APC information and why WebGIS was so important for us. So for some context here, for those that don't know, Winnipeg, right in the middle of Canada, a gateway to the prairies. This is a historic meeting place of two rivers. And right down in the middle of the city where the Assiniboine and the Red River meet is the Forks, which is where the first indigenous communities were. It's where the fur trading posts were set up. That's where the railroads came through. That's where the downtown was built. And the whole Winnipeg was built around that intersection pretty much. One of the jokes in Canada is that all roads lead to Portage in Maine, which is the intersection right in the middle of the city. Because it is in one way true. But nonetheless, like everything else in the city, Winnipeg Transit modeled itself around the same principle. It's a 100-year-old network, a radial sort of hub and spoke design, where they were using a bus mall to do transfers at one location. In 2019, though, by 2019, Winnipeg had been running into some problems. They were causing their own traffic jams. It would take a one-seat ride downtown was very convenient, but if you wanted to go anywhere else other than downtown, there was long travel times and awkward transfers. So they had a bold vision to completely redesign it, which is just come up with something completely new. Obviously, if we're going to be making such grand moves, we need to have a very defensible, data-driven solution. This next slide here is a little snapshot of the APC data. It's a little bit hard to see, but basically, I'm trying to show that these large dots in the middle is where a lot or the majority of the bus activity is happening, right? Downtown at the transfer location, as you would expect. The question though is all the activity happening there because they need to transfer there, or were they to have a different option, maybe a layered grid-based system, would that kind of travel behavior not exist? Then that's when we had to get out of the APC data and get some of the location-based services. So we bought two types of data for Winnipeg. One was origin destination trip data. So for the transportation assessment zones across the city, some 1,100 of them, figuring out what the daily trip rates were, as well as the AM PM peak. And what was especially important for Winnipeg was seasonal variation, because their travel patterns change quite a bit depending on the seasons. So the origin destination you'll see on the left here, whereas on the right, this is the activity density. So that's when a cell phone ping is registered at this location, a 10-meter grid cell, in the given hour of the given weekday or weekend in the given season. That data is interesting. It comes in a couple flavors, whether or not that device is seen at their home location, at a work location, or are they in movement? For example, this is a transient point data set. So it's devices that we're seeing in movement. So from the chart on the left, it did seem that downtown trips weren't as big of a driver as originally thought. And this here's a chart that just compares the transient point activity density with the APC, the passenger kilometers traveled in every sector, which is the cleanest way to see that. The downtown, the bus riders, there's about twice as many of them proportionally downtown than any other, than transportation in general. So that let us, that was the first supporting piece of evidence for the grid-based and layered system. Another sort of interesting thing that this transient point activity can do is sort of enable the analysis of fluctuation by time of day. And I'm not sure if the animation comes through on your end, but you can really get a sense of how the travel changes in a day just through the clustering of points. And here, fall 2018, the Winnipeg hockey team was really on fire. So you'll see in the evening, everyone's getting ready at the game. And then we all went home. So using this kind of data, we put it up on a WebGIS platform, and we were able, as a larger team, to access this platform, turn on different layers, and as like Pragun was saying about equity information or other ancillary planning, data sets, land use, whatever else the study team and the analysts wanted to know. And in that way, we could, as a team, really get into the routing and the network design at a detail level with a data defensible position. Thank you.
Thank you for an interesting presentation and also for being on time. So it's time to move to the next topic, which is estimation and prediction of queues at bus stops using Wi-Fi data. The presenter is Kyung-Sub Ji from Kyoto University. Please share the screen with us. Yeah.
Okay, hello, I'm Kyung-Sub Ji from Kyoto University, Japan. I represent our research topic, which is the estimation and prediction of queues at bus stops using Wi-Fi signal data. We are using Wi-Fi signal data from Wi-Fi sensors for this research. The function of Wi-Fi sensors are that receiving probe requests from Wi-Fi enabled devices in the vicinity. These probe request package are sent to find networks and contain MAC addresses and RSSI, which is signal strength. To anonymize the data, sensor convert the MAC addresses contained in the packet by running a hash function and upload the captured packets to a cloud storage server. Most transit data sources focused on onboard related events, but on a few data sources such as counting or video camera analysis focused on estimating waiting times and boarding demand at stops. That is our motivation, and we are focusing on verifying how accurately it is possible to estimate the queue length at bus stops using Wi-Fi signal data as one of the data sources. Data of this research was collected in Ginkakuji area in Kyoto City, Japan. And Ginkakuji is a famous temple, and we conducted these experiments in peak tourist season for the fall foliage. So we observed the long queue, maximum 80 passengers, and 40 passengers was reached several times in a day. And we used two sensors. One sensor was located at the tops, and another sensor was located on the opposite side across the lower. Wi-Fi signal data can be largely divided into non-randomized and randomized. This randomization is automatically performed in a device to make addresses when a device is searching for a Wi-Fi network. It's much more difficult to trace the device by fixed MAC addresses, and data can be categorized as RSSI and can be categorized as signal strengths. Furthermore, we are able to compare two signal strengths of the same device using the second sensor, stronger or weaker than opposite, and not defeated in the second sensor. Then we can assume that devices whose signal strengths are weaker than opposite are located on the opposite side, not on the queue, and can be eliminated from the data. To conduct linear regression analysis, we firstly set 10 independent variables by randomization and RSSI value. And we conducted the regression analysis for all queues and limited queues. We found systemic difference between non-randomized and randomized MAC addresses. Then we repeated with non-randomized again. In the result, we got negative coefficients, possibly explaining that in longer queues, weaker signals are observed by queue. Then we repeated with non-randomized, but signal weaker than opposite eliminated with second sensor. We found increase in R squared and less negative coefficients with the second sensor. It might be one benefit of using second sensor. From linear regressions, as expected, weaker RSSI more significant for longer queues, and it was difficult to estimate short queues. Next, we conducted ordered load model to focus on long queues. We classified queues into 5 categories: 0 to 9 passengers, 10 to 19, 19, 20 to 20, 19, 30 to 39, and 40 or more, maximum 80 passengers. From the result, classification error ratio was calculated as 0.47. The result model fit shows little increases compared to linear regression model. Precise queue length is difficult to obtain by Wi-Fi sensors, but this study is ongoing analysis, and estimating queues with Wi-Fi signals is some degree feasible. Understandably, relationship between sensor records and queue length requires careful analysis, and site-specific calibration of relationship is also required if similar experience will be conducted in different areas. And for future work, alternative modeling approaches can be applied, such as multiple linear regression model with time series analysis and neural network model. Also, data fusion can be also applied. Data fusion with Bluetooth and Wi-Fi signal data, and a different type of Wi-Fi signal data from the third sensor at tourist site, or counting data of bus arrival time and boarding numbers. And we hope that we can estimate waiting time also with non-randomized Wi-Fi records. Okay, that's all from me. Thank you very much.
Thank you for your presentation on the very innovative use of Wi-Fi data. So now we are also going to change a little bit, and the last presentation is a discussion about users' perceptions of riding using driverless shuttle services. This is based on the use of Twitter data. The presenter is Mahmoud Meshali from University of Toronto.
Hello, everyone. Can you hear me?
Yeah.
Okay, perfect. Thank you very much. Thank you for attending to this panel. So today I'm going to present one of our recent research that we did at the University of Toronto, and also with collaboration with the Canadian Urban Transit Research Innovation Consortium, known as QTRIC. So first, a general background and what is the motivation of doing this research. As you may know, currently there are many pilot programs around the world. So many cities are trying to different perspective of these smart shuttles, and also many cities, they have planned to have it in coming future. But so far we have a limited investigation related to user perception and understanding, especially for these new technologies. From the user perspective, this technology acceptance is kind of critical. So based on that, we used social media analytics tools, because this is one of the cost-effective way to get very high-level understanding about user perception and understanding how we can help our transit agencies or manufacturer to better implement these new technologies. So based on that, the main objective of this study is to understand the public feels toward driverless shuttles, and also to investigate user perception at an aggregated level by directly analyzing this tweets data, and also to explore how user perception and views are different from different locations, and also, for example, people in USA, how they feel about this, using these smart shuttles, and people in European or other countries, how this feeling would be changed over the time as well. So the general methodology that we use here, first, because we are working with Twitter data, we need to do some data management. So we are collecting all the data from the Twitter. We are doing some cleaning out of this data, because this data is mainly and specifically for smart shuttles, and we are not considering data related to AVs, autonomous vehicle, for the private systems. And also we need to do some data segmentation to see where is geographically these data are related. Out of this data, we are doing some analysis as a common practice, semantic analysis, to understand, to see what topic people are talking about. We did some sentiment analysis to understand how people feel about this kind of topic, and we did some spatiotemporal analysis to understand different people from different locations, how they think about this kind of technology. So the data that we collected was from January 2015 until October 2019. We collected all this Twitter data. For the semantic analysis, we defined a lexicon based on 4 major categories. The first category, all the topic related to safety and security are sorted. The second category related to the service delivery. So all things related to that specific category are sorted. Then the third category is information, anything related to the public knowledge, public understanding, and all the data that around these smart shuttles are sorted in this category. And finally, technology itself. Technology means all perspective of this new technology, because this is going to be a new and an innovation way for the future mobility. And for the sentiment analysis, we used some library from the Python, known as text blob, and this is an API that is very compatible with natural language processing. And The score that we are using here is ranging from 0, which means weak sentiment about those topics, and going until 1, which is a strong sentiment for those topics. And finally, we did some spatiotemporal analysis out of all of this data that we are collecting. So jumping quickly about some preliminary results that we are showing here, as you can see, the green bar are positive sentiment, and the red one is a negative sentiment. And you can see that the dot lines are showing the trends. So from 2015 until 2019, we are seeing a kind of, the trend is going to growing negativity and declining positivity, and showing maybe that's growing the skepticism from using these smart vehicles. So if you want to look at that, all this topic in a little bit much more detail, you can see the main challenge for deployment of this shuttle is the understanding of technology itself. But for other topics, we have a kind of balancing between negativity and positivity about deployment of these smart vehicles. So for the spatial temporal analysis we did for different regions and around the world, these are just examples to show how it is going to be changing from 2015 until 2019. For example, USA has one of the highest number of tweets among all the countries. You can see from 2015, we have obviously technology was the main topic that people were talking. And then the second one was safety and security. That was also same for the Netherlands as well. But as we are closing to 2019, the main topic after technology that people are worried and talking about is information. And the last one is the safety and security. So the main finding out of all this analysis, and we want to just summarize them, is our analysis showing that the primary inclination of user is to better understand this technology. They don't worry about other topics or other kind of category at this stage. So user perception have evolved gradually from 2015 to 2019, and it is going to be a little bit negative. Maybe that could be the reason that people are facing reality to understand and to manage their expectation towards the deployment of these smart vehicles. And our analysis showing the first safety and security was the important topic, but as we close into 2019, information was receiving much more attention. And finally, we are thinking that we need to have a plan to address the user concerns, because as I said, one of the main motivation of this study is to increase the public acceptance about these new technologies. Thank you very much, and I'll be happy to have any question if you may have.
Thank you for an interesting presentation on this topic, and we have some time left, so there are a number of questions that have been posted on the Google Docs. Maybe I can try to summarize some of them, basically addressed to all of you. So the first question that came into probably some different forms across was the quality of the data that you have used in the various analyses, and how concerned you are with potential biases that may exist, and or errors, and how do you deal with this type of issues? So the floor is open to anyone who wants to start, but it applies to most of the presentations we heard today.
I'd love to start in on that, but it's certainly a central question for anything that's data-driven. You want to have a measure of uncertainty, or at least some understanding of the reliability. And I feel like there's many ways to do it, but one kind of central approach that I use is multiple data sets. So if you can find the same patterns from different data suppliers, from different data sets, like what if you're looking at job information or travel behavior, or land use, or other kind of more quantitative analysis, you can find more strength in that. But it's only, I mean, the analysis is only as good as the weakest link.
Can I also answer? I would say that the data we are working with, which is data from bus GPS and smart card transactions, is highly reliable. It's very precise, and we haven't found many errors, but there are things that you do not observe. And one big example in Santiago is the problem of fare evasion. Some people don't pay, and we don't observe them. And it is a large percentage of the travelers, and it's very difficult to incorporate them. You can, of course, have independent measurements of flows at stations or bus stop, but it is very difficult to actually incorporate them in all the models that you can develop with the data of those that you actually observe.
Anybody else? There was one question in particular about the use, for example, of the transit app data and whether there may be biases in this data, how concerned you are, and have you identified any?
Sure. So the biggest biases we found is obviously people who use the app constantly or like every day are flooding with the app with the most amount of data. So, you know, someone like the user IDs are anonymized, but of those 300,000 or so trips we ended up with, like 800 of them are from one person. So we tried to like focus less on the raw number of trips that people were planning and more on the number of unique people who were planning certain trips, especially because we were looking at trips that people couldn't make by transit with the existing system. So it's unlikely that someone will try to look up that trip like on a weekly basis, because we don't change on a weekly basis. We change on a quarterly or annual basis. So for what we were looking for, which was these sort of marginal trips that we can't track with our Farebox or APC, focusing on the unique number of people who are requesting trips was more important. Though with the folks who are the heaviest users of the app, I think we could analyze that data for a different purpose. You know, maybe in looking at what do our most like reliable riders do. But for our purposes of planning new service, we did not look at that part of it. But, and just to be clear, the data required a lot of cleaning, because when you use the transit app, say you're in one location and you wanna, you put in an address and it puts the 2 points. Well, maybe the address isn't exactly where you want it to be, so you move it around on the map a little bit. So every time you take your finger off, that's a data point. So we went and we eliminated duplication. So there were actually like millions of trip pairs, but we made sure to look at, like if someone looked up 20 different trips in 1 minute, they were probably trying to get a very specific thing that they were looking. So we would only take the final thing that the final trip pair that they input. So there's some cleaning involved, and there's a ton of data in there, but for what we were doing, it was fine.
Okay, thank you. What about the social media data? Did you find any challenges in those biases, and any experience that you can share with us on that front?
Yeah, I think one of the major tasks for any social media data is data cleaning, and it's taking a lot. So because you are dealing with text, and you should be sure that these texts are really relevant to the topic that you want. And I should say, even you are processing all of them automatically and using some coding stuff, but again, every time you should check that the results are valid and the results make sense. And if there is outlier, be sure that they are not part of the analysis that you want to use. So we should say the majority of our task is data cleaning, I think.
One question kind of related is how representative is the sample of the Twitter users versus the potential population of users?
That's a very good question. I think this is the question for any social media that they want to use. But for this study specifically, we just look at the smart shuttles. And our objective and purpose was that we're going to collect those data that people are actually use those pilot. So people, you know, the pilot program even is not representative for all the population, but a bunch of people are using those pilot programs. And we try to capture as much as possible. But again, this is the kind of limitation for social media data that we are not sure this is going to be enough or not.
Okay, thank you. And there was one question that for Pragun, but also maybe applies to the other talks as well. And that was the question of equity. How is equity measured? How is it dealt with in the data? How useful the data is in addressing equity issues?
Yeah, that's actually a very, very relevant question. So I can speak to the LBS data set that we used. It's a set of data sets. It's a set of products that we have developed using anonymized cell phone data, right? So there is no way to kind of trace it back to the actual user. So there is no way to kind of like definitively know what are the socio-demographic characteristics of those users. But one of the key steps in the analysis is actually looking at the devices which do have sufficient information and trying to infer their home and work locations. And once you've inferred at least the home location, you look at your sample sizes and device penetration rates in these fine geographies in your region, and you see if there are systematic gaps in the data that you're getting. And what we found was that for the studies that we've used the locus data for, there is no systematic gap per se, even for neighborhoods which, let's say, have high proportions of equity information. And there are a couple of reasons for that. One of them, of course, is that a lot of these low-income populations and a lot of these equity-focused populations, their cell phones are actually their primary computing device. And because of that, and the high smartphone penetration rates across the region, we do not see any big gaps in the data set. But that said, we do miss out on certain segments of the populations which are certainly not big users of smartphones. That would be the very young kids, as well as populations that are very senior. So let's say in the 80 or 85 plus range. And these are gaps that are well accounted for. And we know that this is something that we do not capture. And I think for any of these big data sets, it's very important to list out the caveats when you're using the data set. And you need to know that this is not a silver bullet solution for all the questions. But nonetheless, this is definitely very relevant in the current context.
Okay, thank you. Any other comments on that topic?
Yeah, I'd just like to say for the transit app data, even though I think in our recent survey, 80% of our riders have a smartphone, it doesn't necessarily mean that they have a data plan. They may be using Wi-Fi only. But so, when we were doing all this analysis, we were keeping in mind that this is just one of many data sets that we're going to use. It's an extremely helpful one. But many of our riders who may not use the transit app or don't have a phone, we can reach through other methods, through our social service partners and through the city of Cincinnati and other agencies. So it's just keeping that in mind, that you're not seeing everything, but it's still good to have and use. So.
Okay, thank you. I think it's time to wrap up the session, have a short break until the plenary session at 4:30. So thank you all for sharing your research with everybody, and see you later. Bye-bye.
Thank you, everyone.
Thank you so much.
Thank you. Bye-bye.
Bye.